Hello students, today we will discuss about the different codes that are used in spread spectrum communication systems, and there are several properties involved. We will also try to understand the interrelation of the different codes, the fundamental autocorrelation and cross correlation properties, and the key sense of using those codes in different kind of the applications involved in practice. The first kind of the codes which is widely used in practical system design is the Walsh Hadamard code, and we will start with that. But before detailing about this kind of the code generation, Walsh Hadamard code generation, we would like to revisit the usage of the codes. So, the codes spread spectrum communication systems, the way they are used may be broadly classified into two ways. One is for the modulation, we call it the code keying. When codes are used for modulation, then they are done, that code keying is done in this way. You take each and every data symbol of an user or a single connection, one user, and then each of these symbols are then mapped into different codes. So, this symbol will be utilized, he will be utilizing the code 1 and he will be utilizing code 2. So, for several number of the symbols you are having one dedicated codes for that. So, it is a code modulation as if going on. So, it is called code keying. We have utilized this kind of the code keying in a practical system design CDMA 1 or IS 95 mobile communication standard, where in the uplink communication this code keying is utilized. The each and every symbol of a user is mapped into different kind of the codes. Also, the complex valued version that is used, or complex value version of the Walsh code, which is used in your WLAN, especially in 802.11b standard. This is also another example, good example of the code keying. Another kind of the uses. So, code utilized for the modulation is one application. Code can be utilized for spreading also, for giving resilient against the jammers and the interferers, which we are discussing since beginning of this course. Here when code is used for the spreading the spectrum, then all the data symbols of one connection there, or at least the one data packet, they will be spread using the same code. So, data, what is the meaning of a data packet? If I see the structure of a packet may be constituted by the number of the frames. So, let us understand that one packet is suppose having one frame. Then the packet will have mainly the three sections. One is actually the called preamble, where we send the training sequences to synchronize the transmitter and the receiver. And there comes we also utilize some sequences here for our channel estimation. We do AGC automatic gain control also during this period. So, and also the frequency synchronization. So, time frequency synchronization, channel estimation, for all that we send some known training sequence from the transmitter, and the bits associated to that operation we call it a preamble, and all the symbols who are associated is. Second block is constituted of a header section, which is basically the indication about what kind of the modulation you are utilizing for the next data coming, or what kind of the coding you are utilizing for the next data coming. And the rest part of the packet is the payload. Here is the actual modulated data symbols are sent during this section. So, this is the whole packet or a one data packet. So, one data packet does not mean you are only sending the data symbols. It is the constitution of the preamble, header as well as the payload section. So, when we utilize a code to spread the data symbols, at least for one packet, if we keep the spreading code same, then it is actually the spread spectrum. Usually we do not prefer to use different kind of the codes to spread the same section of one within a packet. We do not utilize a different kind of the codes for spreading for different section of the payloads within a packet. So, different codes may be allocated, and for spread spectrum communication you may utilize actually the different code for the different packets, that is true, but usually when it is utilized for segregating the users, then we utilize one dedicated code for one user, and for different users we prefer to provide different kind of the codes to separate them out. So, as the codes we have understood that codes required to be orthogonal to each other. So, the interference from one kind of the code to the next will be minimal, even if actually their transmission time is same. So, users will be differentiated by means of the orthogonal codes they are uniquely utilized for each of them. How the signals from the one user to the next will be differentiated out is such that a receiver will be always multiplying the combined received signal by means of his own known code. So, as the codes are orthogonal to each other, I mentioned that his interference with the other set of the codes, the cross correlation with the other set of the codes over a duration of the symbol duration will be perfectly 0, and you will be ending up with the own signal to be extracted out. That is a dispersing procedure that we have already learned. But these different codes, when they are allocated to different users, we call it is codes are getting utilized for the multi-user communication. So, codes utilized for your spreading for one user to provide resilient against the interference and the jamming is one usage, and then at the same time different codes allocated to the different users, not only they are giving resilience to their from the interference or the jammers, but also it is providing a very good very good kind of protection from the cross from the co-channel interferences, kind of from the co-users or the co-network user kind of interferences. The code length in such a scenario, the way we choose it may be of two types. Either you choose actually the period of the length of a data symbol, or sometimes we choose the length of the code will be much longer than the duration of a data symbol. Where we use which one, the next slide we will learn. For example, the VSF code, the orthogonal the variable spreading factor codes, which we have utilized in the UMTS system, Universal Mobile Telecommunication System. They are exactly of the length of the code is exactly of the symbol duration, but in contrast the precision code that we try to use in the global positioning system, it has a duration of 37 1-week segments. It is having a total period of the 9 months, which we have partitioned for 37 1-week segments, and which is far longer than the duration of a data symbol. And this was necessary because you really do not wish it is a precision that you are asking for the localization in the GPS. We do not prefer anybody to hack the codes, and that is why the length of the codes is chosen so long. And we understand that if you are having a nonlinear codes as well as a very long duration code, it will be very hard to crack the code. Though in the mobile communication system like UMTS or IS-95, a quite long codes are applied. This kind of the codes like the GPS we also prefer to utilize. In UMTS, the gold codes are utilized, where actually the polynomials of m is equal to 25 are truncated. See, sometimes actually we generate a code of very long length, and then finally we can truncate it physically to actually form it in a usable format. And in UMTS, such kind of a gold codes which is truncated with the length of the physical data frame approximately around the 10 milliseconds, and that is utilized in practice. So, in this situation the correlation function of the truncated codes ever will be equivalent to the complete gold codes that we are utilizing. In this slide already we have utilized and we have talked about few kind of the codes. For example, OVSF is one, gold code is another, and so you now know that these are the name of the codes which are most popularly used in practice. We will slowly enter into the characteristics and the generation process of each of these codes today. So, codes of our interest. There are maximal length sequence codes which we have already studied in detail, and the rest are the new to us. The Walsh Hadamard code, orthogonal variable spreading factor code, gold code, Kasami code, and the Barker code. We will learn all the remaining 5 types of the codes, and with the faith that maximum length codes whatever is discussed is well understood. Let us start with the Walsh Hadamard code. Before entering into the generation and the properties of generation mechanism and the properties of a Walsh Hadamard code, let us start with a Hadamard matrix, because the key part of this code generation is a matrix, is a Hadamard matrix. The matrix is a, suppose if the matrix is called H and its order is n, then it is an n cross n matrix whose all the entries will be either +1 or -1, and it has a very unique property that H into H transpose will give you small n into I. I is the identity matrix, and as it is an n cross n matrix, so this I will also be an n cross n identity matrix. So, the construction will be like this. With for an identity matrix, and the T here it denotes the transpose operation on the matrix. So, H into H transpose should boils down to a identity matrix multiplied by the order number. There are several mechanisms and the way we can construct the Hadamard matrix. We will learn them one by one, and finally, we will enter into Walsh Hadamard code. See, suppose A is a matrix which is having its elements A I j, and he is an n cross n matrix. Suppose there is another matrix B which is having his entries with B L k, and this is also an m cross m matrix. Then the Kronecker product of this A and B given by A dot B like this can be given as this all the coefficients of this A multiplied with the matrix B and given by the format written in equation 1.2. The dimension of this guy will be always Mn cross Mn. If now this A and this B both are the Hadamard matrix, so the property says that A dot B, which is a Kronecker product of A and B, and also the B star A, whatever be the way you construct it, it will be also raising another Hadamard matrix. So, this is the first property of the matrix Hadamard matrix, by means of which from 2 Hadamard matrix you can generate the third Hadamard matrix. So, the first this is the first generation mechanism of Hadamard matrix from two other Hadamard matrix of different sizes or different orders. So, suppose A given by this +1 +1 +1 -1, it is an Hadamard matrix with all orders 2 to the power k, where k is always greater than equal to 1. It can be obtained from A repeatedly taking the Kronecker product. So, if A is this, and you can generate the several Hadamard matrices from A by actually simply increasing the order to the power of 2. If k is greater than equal to 1 by the Kronecker product of that, the way we have shown earlier. If B is a Hadamard matrix who is having an order of n, then we understand that A star B will be an Hadamard matrix where A will be given by this, and this Hadamard matrix will have a power of 2n. Suppose A, B, C and D, they are the T cross T symmetric circulant matrix. The circulant matrix always look like this. Suppose you have C0 to C0, C1, C2 dot 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 dot, say suppose Cn minus 1 elements in the matrix. If it is said to be a circulant matrix, then in the next row you should be able to see that Cn minus 1 is here, C0 is here, C1 is here, dot dot dot, you are ending with Cn minus Cn minus 2, and this is the way you will be able to see that this is 0, all the locations, it is circularly, all the elements of the matrix, they are circularly rotating. So, if this is a property, this property is observed, then we will say this is a symmetric circulant matrix. And suppose we are calling that we are having 4 matrices which are T cross T symmetric circulant matrices, and their entries are restricted to be +1 and -1, such a way that if you square them up and add them up, you will be ending up with 4 Ti. And then the matrix, bigger matrix capital M, who is having his entries as M I J, he will be actually a symmetric and circulant matrix if and only if this is a matrix construction going on, and you see that all these elements who are having the, so each and every element is having a symmetric circulant property, and see the way they are moving. Okay. So, if this is the situation, they will be having a symmetric circulant matrix if and only if that happens, and then we can construct a Hadamard matrix from all those 4 symmetric matrices, combining them in this way. So, first row consists of all those T cross T symmetric matrix. Second row will be taken as a minus of this B, and then A minus DC. Third construction will be like this. So, fundamentally you are doing something here, it is actually the ABCD, the matrices, the symmetric T cross T symmetric matrix. Here all are the transpose, and then you are constructing the fundamental matrix. A is shift A. So, you are shifting the fundamental matrix as well as you are taking the transpose of them, and this Hadamard matrix, the way it is constructed here from 4 different matrices which are circularly symmetric, which are having a circular symmetry property as well as a typical dimension given in the last slide. The Hadamard matrix you are ending up with, it will have order of 40. So, cyclic Hadamard matrix now we will enter into, and say for n greater than 1, the only known example that you may have for the circularly symmetric Hadamard matrix, which is order of 4 basically, and this is denoted as H4. See the way the matrix is circularly symmetric is, this was the first element, first row says the first row elements are the Hadamard matrix, and if I rotate it, then it will form the symmetrically shifting, symmetrical form is given, and it is to shift, all the elements are cyclically shifted. So, it is the symmetric nature comes from the fact that you see the upper portion of the matrix, which is exactly the similar to the lower section. Okay. So, this is the way the symmetric property holds good, and that is why we are calling it also circulant matrix, and it has an order n is equal to 4. There are many examples of this n cross n Hadamard matrices H that consist of this n minus 1 cross n minus 1 circulant matrix. See, here is an example. Actual matrix, and in that if you are getting an n minus 1 cross n minus 1 circulant matrix, and if you add the border of the plus ones, you will be able to get an n cross n Hadamard matrix, inside which there is a n minus 1 cross n minus 1 circulant matrix. Let us take an example of another H4. See this H4, this is the fundamental n minus 1 n cross n minus 1 matrix, circulant matrix. See the property, this was plus 1 minus 1 minus 1, it rotated once, this minus 1 came here, plus 1 and then minus 1, you rotate one more and then this minus 1 and one more, rotate it one more and then it will be shifted. So, plus 1 is getting shifted slowly and then this minus 1 first came here and this is shifting here and the last minus 1 is there. So, this section is showing the circulant property, and the Hadamard matrix is constructed by giving a border of the plus 1 on the top and towards the left. Another example, good example is H8. Inside H8 you see this section. These are plus is written because I just because of the size of the matrix we have not written the ones. Basically minus says actually minus 1 and plus says the plus 1, and the way it is moving you see that is a circulant. So, this plus 1 is moved, this minus 1 are moving slowly, shifted one time, you do one more shift and then actually this will be moved for 2 places, similar the 3 places shift, 4 place shift, like that this is going on. And you can construct the Hadamard matrix by adding a border of the plus 1s on the top row and to the leftmost row. So, like that you can check several Hadamard matrix, where you will see the matrix basically is constituted of the n minus 1 cross n minus 1, where n is the order of the Hadamard matrix, and he is consisting of n minus 1 cross n minus 1 circulant matrix inside that. So, these examples which we are calling as a cyclic Hadamard matrix, and they are having basically a 1-to-1 correspondence with the Pele-Hadamard difference sets. So, that is why we are having, sometimes we call it the Pele-Hadamard matrices also. So, all the cyclic Hadamard matrices are basically the Pele-Hadamard matrices, and very good well known examples of the cyclic Pele-Hadamard matrices of the order n is equal to 40. 40 they are having n minus 1 belongings inside, and then n minus 1 belonging to will have any one of these 3 sequences involved in that. For case number 1, see that 40, if the order is equal n is equal to 40. So, 40 minus 1 is equal to 2 to the power k minus 1 will be either type. So, in order to generate this first type of the Pele-Hadamard matrices, we have to have that k should be always greater than equal to 1, and we start from a maximum length sequence. So, maximum length linear shift register sequence, we keep it as a top row, and then we try to go ahead with the circulant of those all m sequences, and this period of the maximum length sequence that you are taking, which is having a relation with k is equal to 2 to the power k minus 1. But remember the maximum length sequence is usually consisting of zeros and ones. So, you have to replace all the zeros by minus 1 and all the plus 1s with the plus 1 only, and so zeros and ones will be represented by the ones and minus 1s respectively, and the way you have constructed for the Pele-Hadamard matrices, you will be ending up with the Pele-Hadamard matrices with this typical relation. So, say the for second type of the situation, to generate the Pele-Hadamard matrix of type B, where P is constituted, P is called as to be a prime number, that will be generated like this. So, for second type of the Pele-Hadamard matrix, for all primes to be 40 minus 1, we will start with the Legendre sequence. The Legendre symbol, where actually 1 by p or each and every one is called a Legendre symbol or quadratic character for modulo 2, which is defines the for a belonging to 1 to p minus 1 by this relation, where each and every Legendre symbol should have either plus 1 or minus 1. For plus 1, it will have the plus 1 if the x square, the quadratic character is coming actually modulo p operation is obtained equal to the value obtained by the modulo p operation for some x. And you start with this by taking the top row to be the Legendre sequence and then start the generation. The third type, to get the twin prime construction of this cyclic Hadamard matrix of the type C, which says that it should have a 40 minus 1 equal to P into P plus 2 equal to P into Q, where this P and Q, these are actually the coprime. These are the twin prime numbers. They are the twin prime numbers, and then we take the top row of this circulant matrix to start with to be from the Jacobi symbols, where these Jacobi symbols A divided by P into Q, whenever this is non-zero element and they will be replaced by plus 1 for A when A is moving from 0 to P minus 1 into Q, and it will replace the minus 1 for all the values of the A which belong to P twice the P to Q minus 1 into P. Remember, actually here if the symbols are said to be completely independent, this P and Q, they are independent and they are not having any kind of their GCD is equal to 1. In that situation, actually this Jacobi symbol can be also written as A by P into A by Q, I mean the multiplication of the two Legendre symbols. And the sequences that we have generated by the type B and type C, they are obviously disjoint, said because there is no prime product, no prime is a product of the two prime numbers. So, they can never be another prime number, and hence B and C are completely disjoint, the generation process itself. Some overlapping may be possible because in the generation type 1 and the generation type C, sorry, A and C, for say example, when the 2 to the power 4 k value is equal to 4 and you are getting it is 15. So, 3 cross 5 is the example where actually C can be generated by means of this, and also the by type A also you will get a 15 length sequence. Now, this is the time with this understanding of different methods of generating the Hadamard sequence. Let us see that how Walsh Hadamard sequence is generated. For Walsh code, we use the Hadamard matrix always, which is having the order of 2 to the power capital N, and this Hadamard matrices are conjuncted to exist for all the orders which are multiple of the 4, and for the powers of the 2, there is a consecutive proof given by J. Sylvester, who showed that the higher order Hadamard matrices, Walsh Hadamard matrix, Walsh Hadamard codes can be generated from the lower order codes. So, this recurring relation we will be using for generation of the Walsh Hadamard code. See, suppose first Hadamard matrix which we are starting is equal to H1, where capital N value is equal to 0. And you are having one element inside the matrix. So, from here the higher order matrix H2 will be generated like this, where these are the same one H1 repeated in the first column and the first row, and the last element will be the conjugate of this. And if I generalize this rule, then for H2n it will be look like this Hn repeated thrice in the corresponding situations, and the last material and the last symbol and the last element of the matrix will be the conjugate of that. So, the Walsh Hadamard codes can be generated from the Hadamard matrix only when actually this can be generated this way when the order of the Hadamard is only the power of the 2, and the rows of the matrix of the order 2 to the power n constitutes the Walsh code, which encodes the capital N bit sequences. So, you can pick up actually the rows of this matrix as a Walsh Hadamard code. So, one such rows will be picked up to develop and to be utilized as a code, a spreading code, and they can be actually utilized to spread an capital N bit sequence. And we can do a very nice exercise at home. So, from H2 onwards you proceed to construct the structure of say H4 and H8, and try to find some kind of the similarities H8 and H16 onwards, and you may try to find out some similarities actually about the fundamental properties of the Hadamard matrix that we have already discussed, whether all those properties are holding good for when it is constructed as a Walsh Hadamard code, because Walsh Hadamard code is a restrictive usage, or it is specially constructed kind of the matrices from the which has the fundamental roots on the Hadamard matrix. So, all the properties of the Hadamard matrix that we have already discussed all should be hold good once the Walsh Hadamard code is generated. So, you may actually try to have a look of all those properties once constructed the higher order values of this higher order Hadamard Walsh Hadamard codes.